Hello, good morning SS2 students. Today we are going to still continue our lesson about the decay graph and also equations. You can open your textbook page 501 and check the question number 15, 16, and 17. After this, I'm going to show you how to do number 15, 16, and 17. So please stick around. Okay, now let's discuss number 15. The isotope nitrogen-13 has a half-life of 10 minutes. A sample initially contains 8 times 10 to the power of 10 undecayed nuclei. Write down an equation to show how the number undecayed and depends on time. So this one actually you can check directly on your textbook, page 500. This is the things that we have discussed yesterday. Then this one, so A is equal to N is equal to N0 times E to the power of negative lambda times T. Next, B, determine how many nuclei will remain after 10 minutes and after 20 minutes. It mentions that the half-life of this nitrogen-13 is 10 minutes. Means that after 10 minutes, the sample will be half of the original. So half of 8 times 10 to the power of 10. Okay, you count it. And after 20 minutes, it means it will be quartered from the original number of undecayed nuclei. For number 15C, determine how many nuclei will decay during the first 30 minutes. Okay, so for the first 30 minutes, we can calculate like this. This is the number of decayed nuclei for the first half-life. This is the number of decayed nuclei for the next half-life. This 1/8 is the number of decayed nuclei for the third half-life. So we calculate by adding it, and then we got 7/8 of total undecayed nuclei from the original undecayed nuclei. So you calculate how much nuclei will decay during the first 30 minutes. Next, number 16. A sample of an isotope for which lambda is equal to 0.1 per second contains 5 times 10 to the power of 9 undecayed nuclei at the start of an experiment. Determine A, the number of undecayed nuclei after 50 seconds. For this one, we can use the formula of the equations of decayed nuclei, which is this one. N equal to N0 times E to the power of negative lambda times T. Remember that N is the original number of undecayed nuclei. And then lambda here lambda is the decay constant and T is the time taken, because the lambda and T already in seconds, so you don't have to change anything. Put in this to your calculator, and then you will get the number of undecayed nuclei after 50 seconds. For number 16, it's activity after 50 seconds. So after we got the N, then we can calculate the activity simply by times the lambda times N. Lambda is 0.1 and then N from here. Then you will get the activity for 50 seconds. Last number 17. The value of lambda for protactinium 224 is 9.63 times 10 to the power of negative 3 per second. Table 31.5 shows the number of undecayed nuclei N in a sample. Copy and complete the table and draw a graph of N against T and use it to find the half-life of protactinium 234. Okay, so you need to complete this table by using the decaying formula n equal to n0 times e to the power of negative lambda times t. Remember that the value of n0 for 40 seconds will be 330, and then following also the value of n0 for 60 seconds will be from this table. For 80 seconds will be from the previous table also. So fill in the table. You can calculate using calculator, and then after that make a graph of n against t. Okay, it will be like this one. It will be exponentially going down, and after you find the graph, then you can find the half-life of protactinium 234 from the graph. Okay, so that's all for today. Submit to me this assignment before 4 p.m. Thank you and bye-bye.